Welcome to Complex Analysis Lesson 14 on contours. Contours are the entities over which we take a complex integral. So we're first going to cover contours in this lesson, and then in the following lessons we'll talk about complex integration. From real valued calculus, we know that the integral is evaluated over an interval, in this case -1 to 3 in our example. So we take the antiderivative of x cubed, which is x to the 4th over 4, and then we evaluate it at 3, and then we subtract the value evaluated at -1, and we get 20 for our answer. So the reason I'm doing this here is both as a review, but also as sort of a prelude to what we're going to get into with complex integrals. And in the case of complex integrals, if you're going between a point, say -1 minus I, and another point 2 plus 3i, there's not just one way of getting between those 2 points. You can take many different paths. They're known as contours, which we'll get to in a minute. Unlike the real valued case where you just have a line segment, there's only one way of getting from -1 to 3. So the problem is much easier in the real valued case. Now also on this slide I have a bit of a diversion. It's not directly related, but I thought it would be of interest to know that real valued functions don't need to be continuous in order to be integrable. The condition is that you need to be continuous almost everywhere, where almost means except on a set of measures 0. So it's kind of an interesting property that's not commonly taught in calculus courses. And if you're looking for an example of that, there's something called the Cantor function, which is a step function that's broken up into many different places, but it still has an integral. And I put the Wikipedia link here in case you're interested in that. As I say, this is a bit of a diversion, but I thought it might be of some general interest since we're on the topic of integrals here. While it is possible to define definite integrals for complex functions, the situation is more complicated. If you're going to define a definite integral of a complex function, say f of z, between points z1 and z2, you need to make clear what is the path that you take between those 2 points. In most cases, it's sufficient to select either a straight line segment or a circular arc. However, a more general approach is usually taken, and that's what we're going to do here. We'll define something called a smooth curve, and we'll put a finite number of those together to make what's called a contour. And on the right, I just have an example here. We want to take the integral from, say, -2 minus I to 3 plus 3i for a given function. It doesn't matter what it is here. I just want to illustrate that there's many ways of getting between these 2 points, unlike the case of real valued integration where you just go between 2 points on a straight line, and there's only one way of getting between those 2 points in that case. Complex integrals are defined over a collection of one or more smooth arcs. And we're going to define that here. A smooth arc is a set, typically a line or a circular arc, but basically a curved line that has such that there exists a function p of t that maps between some real interval AB to the set S. And the function p of t must have these three properties in order for S to be considered a smooth arc. The p of t needs to have a continuous derivative on AB. The derivative cannot equal 0 for t between A and B, and p of t is a one-to-one mapping from AB onto S. So for every value in S, there's a value between A and B, and for every value between A and B, there's a point on S. We also have the case where these first two conditions hold, and this third condition almost holds, except that you have the arc is closed in a sense. You have PA equals PB. So, for example, a circle would be a smooth closed curve. And that's another type of curve that we can use in order to take an integral over. In fact, that's a common case where we take a complex integral over a circle. So this case is also covered. Here we have an example of a smooth arc. It's this line segment here going from minus 2i to 2 plus 2i. In order to verify that this is a smooth arc, we need to have a function, p of t, that maps from some closed interval to the arc in question. So our p of t, we're going to define it to be 2t plus 2ti. You can see here when you put in t minus 1, you get this point here, minus 2i. When you put in t equals 0, you get 0. If you try any of the points in between here, you'll get a point along the segment. And when you put in 1, you get 2 plus 2i. So this point here. We can verify that the p of t it's just the line segment. It's a straight line, and it has a derivative. It's continuous. The derivative is actually 2 plus 2i, so it's a constant, which means it doesn't equal 0, which was the second condition. And the third condition is that it does the mapping that we've shown here in terms of mapping minus 1, 1 to this line segment here. Take, for example, this arc here, this semicircle going with radius 1. We can do two different parameterizations. Actually, we can do more than two, but I'm showing two here just to illustrate a point. We can use polar coordinates and use e to the I theta to define the mapping between 0, pi, and this arc here, this semicircle. You notice when you put in theta equals 0, you get 1. When you put in theta equals pi over 2, you get e to the pi over 2, which is just this point here, I. When you put in pi, you get e to the pi theta, and that gives you a minus 1, which is the point I'm pointing to here. And you also have a derivative that exists, so this fulfills the conditions for a parameterization. The other approach is to use the equation x squared plus y squared equals 1 for a circle centered at 0 with radius 1, and then you let x equal t, you solve for y, and you get the square root of 1 minus t squared, and then you just plug in x and y into our equation for p of t. And you can see here, as you put in, say, t equals 1, you get, this cancels and you just get 1. If you put in t equals 0, for example, you get 0 plus I, that's this point. T equals minus 1, this again cancels and you get a minus 1. And you can try anything in between and you'll get the various points here. So this parameterization also maps in the counterclockwise direction, just as this one did here. And we also have a derivative which exists between minus 1 and 1, but at 1 and minus 1, the derivative is infinite. You have a vertical line here, right? This is the tangent here is a vertical line, and this tangent here is a vertical line. So other than the two endpoints, the derivative exists and is continuous. Directed smooth curves. So the parameterization of a curve, as we've seen, implies an ordering of the points. For our example from a few slides ago, we noticed that when we put in minus 1, we got this point here. When we put in 0, we got here. We put in 1/2, we would get a point 1 plus I. If we put in 1, we get the point 2 plus 2I. So that gives us an implied ordering, and that's what's called a directed smooth curve. If we wanted to change the direction, we would we could define Q of t equals P of minus t. We get this equation here, and then we take t between minus 1 and 1. And you notice when you put in minus 1 now, we get the top point here. You put in 0, you get 0 again. If you put in 1, you get the bottom point. So you're going in the opposite direction. So for smooth curves, there's only smooth arcs, I should say. There's only two possible directions. And we can change from one direction to the other by, if we have P of t going from A to B, we can just define P of minus t going between minus B and minus A. In the case of a smooth closed curve, there's an infinite number of possible directions because of the starting point. And let me just draw, let's just say this is I know I've drawn this horribly, but let's say that's a circle. Then you can pick any starting point on the curve. You can say you can start here, and then you can go either counterclockwise or clockwise in terms of ordering a point, or you could start here or start here. So there's an infinite number of possible directions because of the starting point can be varied. Okay, we've done most of the hard work actually in defining contours. The contour is either a single point, which is kind of trivial, or a finite sequence of directed smooth curves, S1, S2, S sub n, such that the endpoint of these different things coincide. So the endpoint of S1 is the initial point of S2, the end point of S2 is the initial point of S3, and so on. And then putting those all together, we get what's called a contour, and we usually write it this way as a sum. I mean, this sum is not really sum in terms of addition, but in terms of concatenation of these smooth curves. Yeah, and a closed contour is almost the same thing. It's just that the initial point of S1 equals the terminal point of Sn. So you get a closed loop there. A simple closed contour is a closed contour with no overlapping points. So, for example, a circle that would have no overlapping points. If we had like a figure 8, let me draw it here just to make clear. So if we had a contour like that, then it would be a closed contour, but it wouldn't be simple because you have an intersection there. Related to simple closed contours, which sometimes we'll just refer to as loops, we have something called the Jordan curve theorem, which says that every simple closed contour divides the plane into an interior area and an exterior area. Stated a little bit more formally here, every simple closed contour separates the plane into two domains, i.e. open connected sets, each having the curve as its boundary. One of the domains is bounded, known as the interior of the loop, and the other domain is unbounded, known as the exterior of the loop. So it turns out that this is hard to prove. It seems like it's not even worth putting down as a theorem. It seems obvious, but what turns out is that there are cases where your closed contour is something very complex, like a fractal, and it's not so obvious that this theorem holds true in those cases. In terms of history, the Jordan curve theorem was first noticed as needing a proof by Bernard Bolzano. I have his birth and death year here. I couldn't find what year he actually made the conjecture, but he's credited with observing that a proof was needed. There were a lot of false attempts at proving the theorem, and it wasn't until 1887 that Camille Jordan published the proof. After some time, it was thought that this was not a rigorous proof, and other proofs were provided. But then more recently, the claim is that actually Jordan had a valid proof, and so that's the state of affairs. And in any event, the theorem is named after Jordan. I also mentioned here a rather interesting fact. There's something called an Osgood curve invented by Osgood in 1903, which presents some problems in terms of the Jordan curve theorem. I mean, the theorem is still true, but the curve itself has positive area. If you're interested in this, there's actually a Wikipedia article on the Osgood curve. You might want to look into that. It's rather interesting to see the curve that's non-intersecting but has positive area and does define an interior and an exterior as stipulated in the Jordan curve theorem. The Jordan curve theorem gives us a way of generalizing clockwise and counterclockwise. What I've drawn here is a rather complicated curve, and the interior I'm showing here in gray, and the exterior is white. And there's two directions of going around this. You notice here I have a little arrow. Just imagine yourself walking along this path, and you put your left arm out, and if it points towards the interior, then the loop is known as the way you're traversing the loop, I should say, is known as being positively oriented. And if I inverted the arrow going the other direction, then when you walked in that direction, you put out your left arm, you would be pointing towards the white area here, the exterior, and that would be negatively oriented. So positive orientation is a generalization of counterclockwise, and negative orientation is a generalization of clockwise. So we'll see this in some of the examples, although you don't typically take a contour integral over something like this. It's usually just a circle or a semicircle or a straight line. But we still have this need to define the orientation, and that's something afforded to us by the Jordan curve theorem.